I think we are all influenced by Nambu's idea about symmetries, the role, the importance of symmetry in physics. So another title for my talk would be A Story for Symmetry Lost and Recovered. The plan of my talk is as follows. So first I will remind the audience about the fractional quantum Hall effect. And then I talk about the composite fermion, which is an idea that theories have been using to interpret the experimental data about the fractional quantum Hall effect. Then I will talk about an old puzzle that has been in existence for a long time of particle-Hall symmetry. That is the symmetry that had been lost for theory. And I think it has been recently recovered with the notion of Dirac composite fermions. So here is a cartoon of what I would call the theory of everything in fractional quantum Hall effect. We have electrons or some charged particles moving in a magnetic field. Here I write down the Hamiltonian describing such a system in first quantized language. We have the kinetic terms of the electrons and the Coulomb interaction between the electrons. Most of the time I will absorb this factor E into the definition of the vector potential. This, by thinking about this Hamiltonian in perturbation theory, we can understand quite well what is called the integer quantum Hall state. Putting the electron in a magnetic field, the spectrum of each electron is organized into Landau levels, and the distance between the neighboring Landau levels is given by B divided by M. When the density of the electron is equal to an integer times the density of the degeneracy of each of the Landau levels, rho equal n, where n is an integer times B divided by 2 pi, then the system has an energy gap. The energy gap is B divided by M to leading order in perturbation theory over the strength of the interaction. In 1982, the fractional quantum Hall effect was discovered, in which you see non-trivial behavior of the system when the filling fraction is not an integer, but is a fraction. So we define the filling fraction as a ratio of the density of electrons over the density of state on one of these Landau level. Say, for example, we have here 6 states on the lowest Landau level, but we have only 2 electrons. Or we can go closer to the thermodynamic limit, think about 6 billion states in the lowest Landau level and only 2 billion electrons. In this case, the filling fraction would be equal 1/3. Without interaction, we would have a very large ground state degeneracy, which grows exponentially when we take the thermodynamic limit in keeping the filling fraction constant. Experiments, however, show us very interesting properties of such a system. There is a finite energy gap between the ground state and the first excited state for certain rational values of the filling fractions. For example, nu equal 1/3. So before going on, let us describe the energy scales appearing in the problem of the fractional quantum Hall effect. In the integer quantum Hall effect, there is one energy scale, B divided by M, which is the gap in the system. In the fractional quantum Hall case, on the other hand, there are 2 energy scales. The first energy scale is inherited from the integer quantum Hall problem and is still B divided by M. But there is a scale of the Coulomb energy, which is denoted as delta here. It is E squared divided by the typical distance between 2 neighboring electrons. One can take the limit when B divided by M is much larger than delta. As a theorist, for example, one can think about taking m to 0. Then all the physics, all low energy physics will not depend on high energy, higher Landau levels. We can concentrate our attention only to the energy scale that is delta. In this case, the perturbation theory would be useless because there is no kinetic energy. Everything comes from the potential energy. In this case, we have what I would call the standard model of the fractional quantum Hall effect. It is a theory that is valid in the energy scale, which is much smaller than the distance between the Landau levels. The Hamiltonian can be thought of as the potential Coulomb energy projected to the lowest Landau level. One can do this projection explicitly and write down the Hamiltonian in terms of the creation and annihilation operator on the lowest Landau level. I did not write it down, but you can do that, and you can find that the Hamiltonian would be a quartic Hamiltonian in terms of the creation and annihilation operator, which is a very non-trivial problem. There is no quadratic term in the Hamiltonian, only a quartic term. In the next few transparency, maybe 8 or 10, I will describe an idea in condensed matter physics called flux attachment. It is a well-spread, well-used, very oftenly used idea, but sometimes it gives me a certain degree of unease, which I will describe. So the flux attachment is an idea that if we take a particle and then attach a magnetic flux to it, we can change the statistics. Say if we take two fermions and exchange the two fermions adiabatically, we get a factor minus 1. If we now have fermions but assume that they carry 1 unit of a magnetic flux, and assume that these fermions have charge 1, by exchanging two fermions, we get minus 1 times the Aronoff-Bohm factor, which is equal to exponents of I pi in this case, which is in product, it becomes 1. That means that a fermion attached to 1 unit of magnetic flux is a boson. Similarly, if we attach 2 magnetic flux quanta to each of the fermions, the same calculation gives us minus 1 times exponents of 2 I pi, which is again minus 1. A fermion attached to an even number of magnetic flux quanta is still a fermion. The idea of the composite fermions applied to quantum Hall physics can be summarized as replacing the electrons by another object, which we call composite fermions. In the representation of the composite fermion, an electron is the composite fermion with 2 flux quanta attached to it. So let us understand how the notion of the composite fermion can explain some phenomenology of fractional quantum Hall effect. In particular, let us think about the nu equal 1/3 state of the quantum Hall physics. Here I represent the magnetic field threading through the system by a discrete number of arrows. Each arrow corresponds to 1 unit of magnetic flux quantum. You can count here there are 3 electrons and 9 arrows, which means that in the lowest Landau levels we have 9 states, but there are 3 electrons. The filling fraction is equal 1/3. In other words, filling fraction 1/3 corresponds to 3 magnetic flux quanta per electron. We transform then the electrons to composite fermion with 2 magnetic flux quanta pointing downward. These magnetic fields, we will talk later, these are not the same magnetic field as the external magnetic field, but the composite fermion interact with both. with the magnetic field that we turn on externally and with the magnetic field that is that we get by the procedure of flux attachment. Now, in condensed matter physics, there is something called the mean field approximation. Most of the time, it is not a reliable approximation, but in many cases, it gives us a qualitative description of the physics. If we do mean field approximation, we get one, in average now, 1 arrows per composite fermion. We have 9 black arrows minus 6 red arrows to the total of 3. 1 arrows per composite fermions. Which means that the composite fermions in this approximation form an integer quantum Hall state with a completely filled single lowest Landau level. The procedure transformed a quantum Hall problem into an integer quantum Hall problem in which we understand the emergence of the gap more easily. Now let us talk about some less standard situation. For example, nu equal 2/3 quantum Hall state. Here I have 4 electrons and 4 fermions and 6 arrows of the magnetic flux. In other words, we have 3 arrows per 2 fermions. Attaching a magnetic flux quanta to each of these fermions, we get now 8 arrows. So counting the number of arrows in the mean field theory, now we have a magnetic field pointing in the opposite direction compared to the initial magnetic field, with a strength corresponding to 1 arrows per 2 composite fermions. So we have transformed fractional quantum Hall effect with nu equal 2/3 to an integer quantum Hall effect of the composite fermion with 2 field Landau level. Again, we have a gap in this system which tells us qualitatively why the gap appears at this nu equal 2/3 filling fraction. This filling fraction has been also observed experimentally. Using this notion of the composite fermions, most of the observed fraction can be explained. For example, there is a series of filling fraction written in this, which can be written as n divided by 2n plus 1. In composite fermion picture, that maps to filling fraction of the composite fermion equal to n. And nu equal n plus 1 divided by 2n plus 1 would map to composite fermion in a magnetic field pointing in the opposite direction with n plus 1 field Landau level. Previously, we have considered n equal 1 in both of these cases. So these are the plateaus. These are the quantum Hall plateaus corresponding to the fractions that I have mentioned. I will call these fractions the Jane sequences of plateaus. So these are nu equal 1/3, 2/5, 3/7, 4/9, 2/3, 3/5, 4/7, 5/9 from the other side. And in fact, this series seems to continue forever. Now there are samples where you can observe 10/21, at least. Taking these two series to the limit n goes to infinity, we get the filling fraction nu equal 1/2, where we have no plateau. This filling fraction nu equal 1/2 actually is a central plays a central role in the physics of the quantum Hall effect. If we do flux attachment, we cancel exactly the magnetic field. Since we have 2 flux quanta per electrons and we attach 2 flux quanta to each of these electrons in the opposite, pointing in the opposite direction, the total average magnetic fields become 0. When fermions live in 0 magnetic field, they form a Fermi liquid, and the central properties of such a Fermi liquid is that the ground state is gapless. There is no gap between the ground state and the excited state. In this case, we can hope to be able to write down a theory describing the low energy physics of the nu equal 1/2 state. And this has been written down in 1993 by Halperin, Lee, and Reed. The theory, roughly speaking, looks like this theory, in which we have the field psi is the composite fermions coupled to external gauge field and also some internal gauge field. Two main features of this theory that will play a big role in our discussion is the following. First, the number of the composite fermion is equal to the number of the electrons. And that is by construction. We construct the composite fermion by attaching the flux to the original electrons. In the language of the Lagrangian, the coupling of the external A mu field to the composite fermion is the same as the coupling of the A mu field with the electrons. So the current of for example, the charge density would be still equal to psi Decker times psi. Another feature of the HLR, Halperin, Lee, and Reed theory is that there is a Chern-Simons action for the gauge field A. That comes from the procedure of flux attachment. For example, if I write down one equation of motion that follows from the Lagrangian by differentiating the action with respect to A0, I get a relationship between the magnetic field small b and the density of the composite fermion, which embodies the idea of flux attachment. So this is the end of the standard textbook description of flux attachment. But the most amazing thing about the theory of the notion of the composite fermion is that the composite fermion is actually an object that exists in the real world. It's not a mathematical construct. One way to detect the composite fermion is to go slightly away from half filling, in which case you don't have complete cancellation of the magnetic field. Then you can see that there are some objects that move in large circular orbit, and the orbit size increases when you go closer and closer to half filling. It becomes a straight line when you are at half filling. This was done by Won Kang in 1993. I'm showing here a more recent version of the experiment. We put a sample in a periodic potential, and again change the magnetic field so that the circular orbit has the orbit that has size of the same order of magnitude as the periodic potential where the system is put in. We can see resonances when the orbit is commensurate. The diameter of the orbit is commensurate with the wavelength of the perturbation. The composite fermion seems to be real object, real low energy degrees of freedom in the quantum Hall effect near half filling. But despite its success, the HLR field theory suffers from a flaw, which is the lack of particle-Hall symmetry. The particle-Hall symmetry is a symmetry operating on the lowest Landau level. All states on the lowest Landau level can be represented in occupation number basis. We write down, we define the orbital or the solution to one particle Hamiltonian Schrödinger equations on the lowest Landau level, and we can define every state as the linear combination of state in which each of the orbital can be occupied or unoccupied. The particle-Hall conjugation maps such a state in another state in which any occupied orbital becomes empty and vice versa. In other words, it maps an empty Landau level to a full Landau level. It also exchanges the definition of creation and annihilation operators. And one usually defines such a particle-Hall conjugation as anti-unitary transformation. Obviously, the filling fraction nu maps to 1 minus nu in this case, after the particle-hole conjugation, since we exchanged the notion of particle and holes. In particular, a half-filled Landau level maps to, again, the filling fraction nu equal 1/2. A half-filled Landau level is at the same time a half-empty Landau level. One can show also that in the lowest Landau level limit, in which the only term in the interaction is a quartic term, encoding the information about the interactions, particle-hole symmetry is an exact symmetry of the Hamiltonian. It commutes with the Hamiltonian. But in the composite fermion theory, there is no sign of such a symmetry. For example, if we look at the filling fraction nu equal n divided by 2n plus 1 and nu equal n plus 1 divided by 2n plus 1, which should map to each other under particle-hole symmetry, in the composite fermion picture, they look very different. For example, the nu equal 1/3 state corresponds to one filled Landau level of the composite fermions, while the nu equal 2/3 state, as we have seen previously, mapped to two filled Landau level of the composite fermion. And that distinction remains when we go to higher and higher n in the Jane's series. Thinking about particle-hole conjugation for the composite fermion Fermi liquid at half filling is even stranger. Naively, if we think about particle-hole conjugation, we take a filled state and make it empty. For example, here I have a Fermi sphere, a Fermi disk in 2 dimensions of composite fermions. Under particle-hole symmetry, naively, one would have a hollow disk. All the state outside the Fermi sphere should be filled, and all the state inside the Fermi sphere should be empty. Obviously, it is nonsense. A related question is that there is no description of the anti-Pfaffian or no simple description of the anti-Pfaffian or the anti-Moritz state in nu equal 1/2. The particle-hole asymmetry of the HLR theory has been noticed very early on in paper by Kivelson and collaborators and others. And this issue periodically came up in the literature, but there has never been a conclusive resolution of the paradox until very recently. The issue came up sometime with better understanding of the physics of the quantum Hall effect. For example, in 2007, Michael Levins and collaborator and also another group found an anti-Pfaffian state by thinking very carefully about how the Pfaffian state transformed under particle-hole symmetry. And actually, these papers are the paper where I have learned made me start thinking about particle-hole symmetry in the quantum Hall effect. Why particle-hole symmetry is difficult? Particle-hole symmetry is not a symmetry of the theory of everything, at least for non-relativistic particles. It is not a symmetry of non-relativistic fermions in a magnetic field. In fact, the theory of a non-relativistic fermion in a magnetic field has only one discrete symmetry, which is the combination of spatial reflection and time reversal, which is not particle-hole symmetry. Such a symmetry only appears after the projection to the lowest Landau level, which we have called the standard model of fractional quantum Hall effect. And so it is not realized as local operations on local fields as the symmetries we are accustomed with in field theory. Now, thinking about what may happen, we have three possibilities. The first possibility is that such a symmetry may be a hidden symmetry of the HLR theory. Although the HLR theory looks particle-hole symmetry breaking, in fact, if we do calculation carefully, the particle-hole symmetry would reappear. Kivelson and collaborator in 1997 did quite a careful analysis of the HLR theory, and they don't see such a possibility appearing. Another possibility is a spontaneous breaking of particle-hole symmetry. And that would be probably, from the point of view of condensed matter physics, a worst-case scenario, because here we don't have the symmetry, and the particle-hole symmetry is, in the real system is only an approximate symmetry that appears after projection to the lowest Landau level. So that would mean that there is no particle-hole symmetry at all. However, by now, I think we have considerable numerical and some experimental evidence against this possibility. The third, and I think the most interesting possibility, is that the correct theory is a different theory, which realizes particle-hole symmetry in an explicit way. It's not an HLR theory. And that is the theory, that is the idea of Dirac composite fermion that I proposed about a year ago. At the level of the half-field Landau level, we have the Fermi disk of the composite fermion. Under particle-hole symmetry, this Fermi disk should map into a Fermi disk. It cannot map into a hollow disk. Particle-hole symmetry should map a composite fermion to itself. But it also should reverse the sign of the momentum of the composite fermion, which you can see by just looking at how the total momentum changes under particle-hole symmetry. So the idea is that the composite fermion is a massless Dirac fermion, and particle-hole in 2 + 1 dimension, and particle-hole symmetry acts as time reversal for this composite fermion, mapping a quasi-particle with momentum k into another quasi-particle with momentum minus k in a certain basis, in a certain Dirac basis. Psi would map to, for example, I sigma 2 times psi with the sign of time reverse. It's antilinear operator. The first hint of the Dirac nature of the composite fermion can be a glimpse by thinking about it's a psi in the, if we think about action of time reversal on operators, on second quantized operators. So the thing is that, could I go back a slide? T squared is minus 1. Yeah, it maps a particle into its own, into the particle. The chemical potential is invariant under particle-hole symmetry. So, for example, it's not charge conjugation in which you would replace psi by something times psi star. As particle theorists, I usually avoid thinking about antilinear transformation line time reversal. But here I think, as I will tell you, there is advantage in thinking about this kind of transformation. In fact, I could have defined particle-hole symmetry in a unitary way, but then I will lose some of the strength of the argument.
Are you saying that this particle-hole symmetry acts in one variable is time reversal and the other variable is not like time reversal?
Exactly.
How can it be that you change variables and change the commutation relation of your operation to time reversal?
This is not the same variable as the electrons. It's completely different fields.
The theory has an operator that implements particle-hole symmetry.
Right.
And another operator that implements time reversal symmetry.
Time reversal is not a symmetry of the problem.
The transformation.
Yes.
You can ask, do the two operations conduce or not?
This theory doesn't realize time reversal.
I'll ask you differently. Neither theory has time reversal. This one has a symmetry that acts as time reversal.
Right.
If you change variables, it does not act as time reversal.
So it's
whether a symmetry does or does not act as time reversal is independent of which variables we use.
time reverses. In the previous definition, the particle-hole symmetry is an anti-linear operation that maps the nu to 1 minus nu and t to minus t. Time reverses sign under the particle-hole conjugation. So there is no problem here, I think. We can discuss later.
Whether a transformation is time reversible or not is independent of which variables you use.
It depends on the language that you use. Here I use the language. Here you can think about. You don't have to think about this as a particle time reversal. I could have just erased this from the slide. I defined a discrete symmetry that I will show explicitly how it acts on each of the fields in the effective theory that I will show. And I compare how psi transform with Peskin and Schroeder. And I found that in Peskin and Schroeder, this transformation is called time reversal. But in the theory that I consider, that would be particle-hole symmetry. Yeah. Yeah. I can, yeah, maybe it's a somewhat a careless, not very careful way to write the transformation. But what I mean is that you take the Lagrangian, you take the action, and you do this into the action, replacing psi by this, and then all the other I replaced by minus I, you get the previous action. Yeah. So the first hint of the Dirac nature of the composite fermion is the following. We know that nu equal n divided by 2n plus 1 map to the composite fermion filling n Landau levels, and n plus 1 divided by 2n plus 1 map to composite fermion filling n plus 1 Landau level. How about trying to reconcile these two numbers? And the most naive way is to take the arithmetic average of the two numbers. I mean, we get n plus a half. Clearly, there is a problem in this way of thinking. The composite fermions are supposed to fill an integer, to form an integer quantum Hall state, which usually corresponds to an integer filling fraction. And here we have a half integer filling fraction. But that is a standard situation when the fermion is a massless Dirac fermion in 2 plus 1 dimensions. And actually, this fact has been seen experimentally when people, after graphene has been made. One of the first experiments with graphene was integer quantum Hall experiment, in which we see beautiful steps, integer quantum Hall steps, and if we divide the whole conductivity by the degeneracy of the Dirac fermion, in this case 4 because of spin and what we call pseudo spin, we get sigma xy equal to n plus 1/2 times the usual quantization coefficient. Theoretically, the way to think about this is to think about the Landau levels of massless Dirac fermions in external magnetic fields. The Landau levels form there are negative Landau levels coming from the Dirac sea, and there are positive energy Landau levels. They are symmetric under changing E to minus E. And so we expect that the steps, the quantum Hall steps, should also be symmetric around 0. And that's how it happened here. Filling one, the 0 energy Landau level take us from filling fraction minus a half to plus a half, not from 0 to 1 or minus 1 to 0, which would break the symmetry of the spectrum with respect to charge conjugation. Another way to think about, another way to argue that particle-Hall symmetry has to be looks like time reversal at the level of the composite fermion is to think about the particle-Hall conjugation square. Okay, that under particle-Hall conjugation square, a state mapped to itself. But the square of the antilinear transformation can be plus or minus 1, and we have to determine the sign by explicit calculation. So that explicit calculation can be done quite easily. We just look at the definition of the, we have to look very carefully with the, at the definition of this transformation, and we can convince ourselves that theta square is equal minus 1 times m minus 1 divided by 2, where m is the number, is the degeneracy of the Landau level. That formula may be not very illuminating, but let us accept one formula from the standard composite fermion picture. That is, the number of composite fermion is half the number of flux quanta. If we are in the nu equal 1/2 state, that would be correct. M is equal 2 times the number of composite fermion. This formula becomes a very intuitive formula. Theta square is equal minus 1 to the number of the composite fermion. If theta acts as textbook time reversal on Dirac composite fermions in 2 plus 1 dimension, this psi would map to minus psi under theta square. So theta square would be a linear. Yeah. Mm-hmm. In the level of the wave function, that's usually I would define time reversal. But I think there is a, whatever, if we do calculation carefully, we would get this relation, which is most important for our discussion. And for Dirac composite fermion, theta square is known to be minus 1 to the power of the number of the composite fermion. So that gives us a problem with flux attachment. For an even number of the orbital on the lowest Landau level, we have seen that theta square acting on any state is equal minus 1 to this m divided by 2 to the same state, independent of whether that, how many electrons is there in the in that state. The factor depends only on the magnetic field, not on the number of electrons. So in order to have a consistent assignment of particle hole symmetry in the composite fermion theory, the number of the composite fermion has to be equal to half the degeneracy of the lowest Landau level, which does not coincide in general with the number of electrons. For example, away from half filling, the number of composite fermions should not be equal to the number of electrons. And that goes completely against the philosophy of flux attachment, in which there is an intuitive picture of how the composite fermions appear from the original electrons. Tentatively, the theory of the lowest the low energy effective theory of the lowest of the nu equal 1/2 state should look something like this. We have a massless composite fermion coupled to a gauge field, a dynamical gauge field, which can mix through a Chern-Simons term with the external gauge field. Instead of flux attachment, somehow this psi field should appear. I think it would appear through some equivalence of particle vortex duality, but acting on fermionic field. Yeah. Sigma xy is 1/2. This is. In this case, it should be there. In the case of the Dirac composite fermion. Yeah, but I'm going to. Yeah, I'm confused myself about that, but I think what we can define here is that psi would be a fermion that lives on the domain wall. Should be defined as a field that lives on the domain wall, in order to avoid and A as well. A should. So this is something that I'm not going to to say anything, because one of my statements may contradict the next. So but I think the idea here is the following. The central idea that I want to tell you is that the composite fermion has to not appear from the procedure of flux attachment, as we understand, should appear through some particle vortex duality. It is a known duality in the case of boson, and in the case of fermion would be new. Psi has to be a massless Dirac fermion, because a mass term for such a fermion would break all the discrete symmetry. So we have to define this theory in such a way that we have a discrete symmetry, and I think one can define it. At least for, if we don't think about the configuration of little a that can have monopole in it, then this should not be a problem. ADA and the fermion mass would break particle hole symmetry. Let's talk about that maybe later. Yeah. The gene sequence would not be affected if one think about this theory. And the idea, this is a non-trivial fact. We have to make two modifications, roughly speaking, to HLR theory. One, to transform the non-relativistic electron into relativistic massless electron. And the other one is to throw away a Chern-Simons term. And they cancel each other in the chain sequence. The particle vortex duality should work in a way that maps the magnetic field of the original electron, of the original acting on the original electrons into the density of the composite fermion, so that in a finite magnetic field we still have a Fermi surface of the composite fermion, which is required by by experiment, and it should map the density of the original electrons. More precisely, the density of the original electrons measured from the half field point to the magnetic field of the composite fermion. And so nu equal 1/2 state would correspond to a finite density of the composite fermion in a magnetic field 0. If we write down this action and then try to compute the current and the density of the composite fermion, you see exactly how this map, the exchange of the notion of magnetic field and the density is realized. One consequence of the Dirac composite fermion can be thought of as follows. So if I define an operator which is particle hole symmetric, it cannot be the density of electrons, because that would change sign under particle hole symmetry. But I can define, for example, this operator, rho minus average rho times grad rho square. One can show that the matrix elements of this operator between a state and its particle hole conjugate minus k is 0. And that manifests itself into something called the suppression of Friedel oscillation in the correlation function of this operator. So here is the most non-trivial test of the Dirac nature of the composite fermion. You measure numerically the correlation function of this operator, and you should see no sign of Friedel oscillation if particle hole symmetry is exact. And that is what is seen. Different curves in this by these authors. Different curves here correspond to different degree of breaking of particle hole symmetry. And you see that when particle hole is unbroken, the curve becomes flat. There is no sign of Friedel oscillation. Various other consequences of particle hole symmetry can be derived. Thank you. They are not necessarily a sign of the Dirac nature of the composite fermions, but would be a sign of the fact that we have particle hole symmetry. So, for example, the conductivity that we can measure experimentally, sigma xx and sigma xy, at exact half filling in the presence of particle hole symmetric disorder, sigma xy has to be equal a half of the quantum. E square over H. HLR theory, the HLR theory give you some prediction that a version, most used version of the HLR theory would give you rho xy equal 2, which is not the same as sigma xy equal a half if there are diagonal matrix elements in the conductivity matrix. Another consequence is that one of the thermoelectric coefficients, namely the diagonal coefficient, alpha xx, has to be equal to 0. Again, the simplest version of the HLR theory would give you alpha xx, which is non-zero. This prediction was made by Porter, Sabin, and Vishwanath recently. We heard from Peter Freud that Nambu was greatly influenced by Japanese philosopher of science, Taketani, who listed 3 stages of scientific development, from phenomenon to substance to essence. The phenomenon in this case would be fractional quantum Hall plateaus. The substance is composite fermion, the notion of composite fermion which we distill from the experiment. But the essence, I think, is something that we are still trying to explore. I think it is some version of fermionic particle vortex duality that act in a certain class of theories in 2+1 dimension. That contain, in this case, would be a theory that contains only fermions but no bosons. How to get there is something that is currently being explored. Shankar Murthy showed how to realize the so-called Gerwin-McDonald-Platzmann algebra from the Dirac fermions, possibly Dirac composite fermions. Another very active topic of research right now is the duality on the surface of topological insulator at 0 magnetic field. This is related to the physics of the Lewis-Landau level. In particular, in the external magnetic field, you can argue that there must exist state on the surface of topological insulator similar to the fractional quantum Hall state. The idea here is that QED3 in some version may be equivalent to the theory of free fermions. QED3, so the free fermion would be a theory of the original electrons, and QED3 would correspond to the theory of the composite fermions. Maybe this duality can be obtained from supersymmetric duality, but there is a problem of how to get rid of the bosons. There is a question that there are a set of questions that one can ask: how this symmetry, how this duality may be consistent with general principle, like anomaly matching, which I don't understand quite well here in this case, or spin charge relation, the relation that in a theory corresponding to electrons, the spin, half integer spin should have should have odd charge. Experimental progress is underway in trying to understand if the composite fermion is the Dirac fermion. Thank you very much.
We have plenty of time for questions.
This is asked really out of a position of ignorance, but in describing composite fermions, it sounds like it's sort of done as a counting and a heuristic, and I was just curious to what degree there's dynamical support for the idea of composite fermions.
There is some dynamical support. There is experiments measuring the attenuation of surface wave in nu equal 1/2 state, and that can be related to, you can compute, or at least try to compute it using the HLR theory as a low energy effective theory, and you get results that can explain the experiment.
But the HLR theory is just postulated rather than derived.
There is no derivation except for, at least from my perspective, all the derivation that was made in the literature is based on the mean field approximation, which is not a reliable derivation. The work of Alicia, Essin, Mroz, and Motrunich is probably closest to derivation of the theory, but they relies on a discretization of the theory in one dimension. Once you discretize the theory in one dimension, you can change. You have a change of fermions, which you can bosonize. After bosonization, you can apply some trick and then refermionize again the resulting theory. There is no derivation that is done in the continuum.
Are you aware of any issues with the composite boson theory of the fractional quantum Hall space?
I'm not. The composite boson theory.
Yeah, of the fractional quantum Hall space, you can't get, that's the original theory of it was 1/3.
Right. The composite boson doesn't have particle hole symmetry, unless it's hidden somewhere. It doesn't have particle hole symmetry.
We talked about it, yeah. The second bullet talks, the last line. So the second bullet, I'm very puzzled at how that would be true. The free fermion system is time versus QED3 doesn't. How can they be equal?
I heard from you that you have an idea about this. It might be
I have lots of ideas, but it's not this statement. This statement,
your name doesn't appear in this statement, but the idea of one of the idea would be the following: we define some QED3 living, say, on the surface of a domain wall. Let me make one of the example. So suppose you have a single Dirac particle living in a domain wall in 3+1 dimension. So this fermion would live in 2+1 dimension. It's coupled to a gauge field, which somehow are confined, a U1 gauge field confined on both sides, and so also would live only in 2+1 dimension. In this way, the theory looks like a single fermions coupled to a gauge field, but it is a QED3, but defined in such a way that it is that is of time reversal invariant.
I think my question was same as Nati's, because this duality refers to just a single two-component Dirac fermion, right? That has a parity anomaly, so you have to add something like k equal to 1/2. Is that
So if I have,
right?
I can tell you a lot of confusion about that. I'm sure this theory is correct based on the experimental and the argument about the symmetry. If I define this A as with a factor of 2 here, I would not have the problem with parity.
Oh, so you're talking about charge 2.
However,
a single charge 2 fermion.
However, I have a problem. If A is a compact gauge field, then I have monopole events that changes the conservation of a quantity that I would call the density of the electrons. But in the theory of the electrons, the density of electrons should be conserved. So I have to suppress this monopole event. So I would tend to think that this A mu is a non-compact field. One solution that is proposed by Metlitsky and Vishwanath is that this A mu is a compact field, but with 2 different compactification radius when you put on a torus. What does that mean?
Usually in theories of H, you think the normalization, there's only one normalization. If you don't change that, you change problem.
That's what they say. I believe that there are a lot of things that we don't understand. I don't understand. I believe that there are a lot of things I don't understand. But I believe that there is a argument that the theory, the final theory, must be a version of QED, some kind of QED, defined in such a way that the symmetry, all the symmetry and the parity anomaly matches with the original theory. The confusion that I have right now is that when I try to do one thing, the other thing doesn't match, and the other way around.
I mean, if I understand correctly, this nu equal to 1/2 theory is a theory with no mass gap, right?
It's a theory with no mass
So
gap.
Is it a conformal field theory?
It's not a conformal field theory because the radius of the Fermi sphere doesn't scale when you do renormalization group. You have a single scale. The degrees of freedom live not near k equal to 0, but at some given k. So, for example, Polchinski and Shankar developed a renormalization group in which you have to increase the number of fermionic flavor when you go to the infrared. The number of patches on the Fermi surface increases in the infrared. So, but it is a theory which seems to be well defined. At least the object exists. But here you have to consider this theory in the background. So in a finite magnetic field, there is a density of these fermions. So again, you have a so the composite fermion is the theory of Fermi surface coupled to a gauge field. And that gauge field mixes with the external field. Yeah.